Hello everyone. Today we are going to start talking about integration. Uh, this is chapter 7.8 in the textbook. We've learned how to compute derivatives of functions of more than one variable, which is partial derivatives. So we've learned how to take partial derivatives with respect to one of the variables. So similarly, it shouldn't be surprising that we can integrate with respect to one of the variables. For example, suppose we have a function which depends on two variables, x and y, equals, say, 2xy. Then we can integrate this function with respect to the variable x, say from 1 to 2. Just like when we were taking partial derivatives, when we were taking partial integrals, we treat the other variable as a constant. So this becomes the integral from 1 to 2, 2x, y dx. And we treat the variable y as a constant here. Now the antiderivative of 2x is x squared. Therefore, if we consider y as a constant, the antiderivative of 2xy would be y times x squared. So it's y times x squared evaluated from 1 to 2. And remember that we are integrating with respect to x, so we plug the boundaries 1 and 2 into x, not y. Okay, y is considered as a constant here. So we plug 1 and 2 into the variable x, and we obtain 4y minus y, which is 3y. Okay, so this is all pretty similar to the standard integration, the one-dimensional integration. However, in this case, since notice that the answer is actually a function. The answer from this partial integral is not a number. It's actually a function with respect to y. So that's what you should keep in mind. If you have a function f that depends on two variables x and y, then if you integrate with respect to x, you get a function that depends on y. If you integrate with respect to y, you get a function that depends on x. Okay? Now, it should be noted here that when you are taking partial integrals, the boundaries, they don't have to be fixed numbers. They don't have to be like 1 or 2 in this case. It can be values that depend on y. For example, we can choose the integral to be we can choose the domain of the integral to be from 1 to 2y. Okay? Because we are integrating with respect to x, so there's really no reason why the upper bound cannot be chosen as a term that depends on y. Okay? So the computation is very similar. Let's go through it together. It's the integral of 2xy. Just like we did the last time, the antiderivative is yx squared. The only difference here is that now we're evaluating this from 1 to 2y. So we plug 1 and a 2y into x and get y times 2y squared minus y times 1 squared, which is 4y cubed minus y. Okay, so keep in mind that when you're taking partial integrals, uh, the boundaries can depend on the variable that you are not integrating over. Okay, but for example, if you write 2x in the boundary, then it doesn't really make sense because you're integrating with respect to x. Then x cannot be in the boundary, but y is fine. Okay, let's see another example. This time, let's integrate with respect to y from 1 to x, and then 2x squared y to the minus 2, and then plus 2y dy. Once again, this is a function that depends on x and y. Since we're integrating with respect to y, it's perfectly fine for x to be in the boundary. All right, so let's take the antiderivative of this. Now, since we're integrating with respect to y, we think of x as a constant, right? So the antiderivative of the first part would be 2x squared times y to the minus 2 plus 1 divided by minus 2 plus 1. This is how we find antiderivatives of exponentials. We add 1 to the exponent and divide it by the new exponent. And of course, the antiderivative of 2y would be y squared. And this whole thing evaluated from 1 to x. Alright, and then let's plug 1 and x into y. When y equals x, you get 2x squared times y to the minus 1 divided by minus 1, and then plus x squared. Minus, plug 1 into y, we get 2x squared. Oh, sorry, that's not y squared. That's not y to the minus 1. That's x to the minus 1. Alright, times 1 to the minus 1 is, again, 1, divided by minus 1 plus 1. Okay, so we get minus 2x squared times x to the minus 1. You get minus 2x, and then plus x squared. Minus minus cancel out, so we're left with plus 2x squared, and then minus 1. So the answer is 3x squared minus 2x minus 1. All right, this is how partial integrals are defined. Oh. All right. Next, if we go back to the last example, we're integrating a function that depends on x and y. So let f of x and y be a function of two variables. Then the integral from, say, arbitrary function g1 of x, g2 of x, f of x and y, dy. Remember that I said when we're integrating with respect to y, x can be in the boundaries. So this is just a general formulation of the integral with respect to y, saying the boundary can be any function that involves x only. All right. So this integral is a function of x. Right, so going back to our last example, when we're integrating this function with respect to y, we end up getting a function that depends on x. So we know this integral is a function of x. If it's a function of x, we can integrate it again with respect to x. So with respect to x, say from a to b, and obtain the integral from a to b and this big thing Okay, so this is what we got earlier, and it is a function of x, so we can integrate it from a to b and write it this way and obtain some number. Notice that the inner integral, as we said, it gives you a function of x only, that it does not contain y, so the boundaries for the outer integral, since it's a function of only one variable, it just has to be numbers. Okay, and this is what we call a double integral. So essentially, you just have a function that depends on two variables and you integrate them with respect to each variable. And the result is a double integral. And of course, you can change the order of integration. You don't have to integrate with respect to y first. Uh, if you integrate, say, with respect to x first, so the boundary are some other functions that depend on y, and let's pick some other numbers for the boundaries of y. This is also a double integral. All right, and as you'll see later, I'm not sure if we can get to it today, uh, but you'll definitely see either today or the next lecture. Um, if you're given an integral in this form, say if you're given an integral with respect to y first, then x with some known boundaries, there are ways to manipulate it and change the order of integration and end up with the integral with respect to x first, then y. So the only difficulty lies in finding the correct boundaries for the new integral in order for these two expressions to be equivalent. I.e., if you're given g1, g2, a, and b here, there are ways you can find the numbers c, d, and the functions h1, h2 such that these two double integrals are equivalent. All right, let's do an example on the double integral first. Practice problem. Evaluate the integral from 1 to 2, and then from 0 to x, 2xy plus 3 dy dx. Okay, so we compute the inner integral first and leave the outer one as it is, so 1 to 2 and then dx. The inner one, when integrated with respect to y, x is a constant, therefore we get xy squared plus 3y. And this is evaluated from 0 to x. Plug x into y, we get x cubed plus 3x plus 0 into y, we just get 0, so minus 0 dx. Right, and the antiderivative of x cubed is x to the fourth divided by 4, and then plus 3x squared over 2. And this thing evaluated from 0 to 2. Plug in 2, we get, 1 to 2. That was a mistake. So evaluated from 1 to 2. Plug in 2, we get 2 to the fourth is 16. So that's 4. And then plus 3 times 4 divided by 2. That's 6. then minus 1 over 4 minus 3 over 2. And that's 10 minus 3 over 2 is 6 over 4, therefore minus 7 over 4. And the answer is 33 over 4. All right, let's try another one. Integrate 1 to 2, and then 0 to x, 5x squared y minus 2 dy dx. So we do the same thing. Evaluate this integral first. We get 5x squared y squared divided by 2 minus 2y from 0 to x dx. If if you find this confusing, like when you have two boundaries, but when you have the boundaries, but you have two variables, you're not sure which one you plug it in. You can write, for example, y equals 0 and y equals x to make this a little bit clearer. Here, I'm going to neglect that. But if you find yourself sometimes confused over which variable you're plugging this into, it might be good practice to write y equals 0 and y equals x. Anyways, plug it in, we get 5 times x to the 4th divided by 2 minus 2x, and then again minus 0, and dx, and that is x to the 5th over 2. This is 1 to 2, sorry, minus x squared. Evaluate it from 1 to 2. Plug these numbers in, we get 2 to the 5th is 32, therefore 16 minus 4, and then minus 1 over 2 plus 1. Therefore, this is 12, 13, 13 minus 1 over 2, that is 25 over 2. Alright, so this is how we evaluate double integrals. It's pretty straightforward. You're essentially just doing integration twice. Now let's talk about how why are double integrals useful? Well, first we can use it to find the area of some shape in two-dimensional coordinate system. So suppose we have So suppose we have this. This is the first one. This is the first diagram I'm going to draw. And this is, let's say, g2 of x. This is a y coordinate. This is x coordinate. Okay. This is g1 of x. This is x equals a. This is x equals b. Then the area bounded by these two curves and these vertical lines, area bounded by g1 of x, g2 of x, and then the two straight lines, x equals a, x equals b, is the integral from a to b, and then the integral from g1, let me move this a little lower so that we have some space, from a to b, and from g1 of x to g2 of x, dy dx. So the integrand is just 1, all right? It's just 1. Or we can neglect the one. The one doesn't have to be written out explicitly. All right, so this is the area bounded by these two curves. Remember that in probably 16b, you've seen how to find area using a single integral, which can be easily obtained here. Notice that since 1 is a constant, it's a constant function, and we can evaluate this inner integral to be oops. A to b, the integral of 1 is just y, evaluated from g1 of x to g2 of x dx, and from this equals g2 of x minus g1 of x dx. So this is exactly what you've learned before in 16b or maybe 16a, how to set up an integral to evaluate the area bounded by these 4 curves. But here we introduce another definition, which is or another expression, which is formulated by double integral, where the integrand is just a simple 1. Okay, but you'll see that these two formulations give you the exact same result. It's you can actually change this double integral into a single integral with this one very simple step. All right, so what if we have an area bounded by say this is h1 of x, this is h2 of x, I mean y, know that these two curves are they go up and down, so it means they can be expressed as x equals some x1 of y, right? And two horizontal lines, y equals d and y equals c. Then the area in between can be written as the integral from c to d, and then from h1 of y to h2 of y dx dy. All right, so if if the shape looks something like this, then we integrate with respect to x first and then y. If the shape looks something like this, then we integrate with respect to y first, then x. Why? Because it's very simple. I mean, if the shape is something like this, then we realize the upper bound and lower bound of the shape are not straight lines. They're functions that depend on x. Therefore, you must integrate with respect to y first. When you integrate with respect to y, you get a function that depends on x, and then you can integrate that from two known fixed constants, a and b, and everything will work out fine. Similarly, since the left and right bounds for this shape are functions, then we integrate with respect to x first. Okay, and again, this also equals the integral from c to d, then h2 of y minus h1 of y dy. All right, even though this is even though the double integral has integrand 1, which easily reduces to this single integral, but in this class, when you're computing, when you're for the next couple web work assignments, when you're asked to compute, or in the web work assignments, either in the web work assignments or in the quizzes, when you're asked to compute these areas, write out the double integral first, because we're learning double integral. Although finding the area of some shape is not the main application of a double integral, but it certainly is one, and we use that. We can compute that with integrand 1. And probably in the next lecture, we'll see some more practical applications of double integral. For example, you can find volume, or maybe even use density to find weight or something, if the shape is flat. Okay, next, let's do 2 practice problems. First, this is a very simple problem. Let's try to find the area of the rectangle one smaller than given by this. X is between 1 and 5, and Y is between 2 and 4. Now the area is of course easily calculated. It's just 5 minus 1 times 4 minus 2. But let's try to set up a double integral to represent the area and compute it that way. Alright, if you want to graph it, then it looks something like this. From 1 to 5 and then 2 to 4, so probably something like this. Alright, this is 2, this is 4, this is 1, this is 5. Okay, the integral to represent the area here would be the integral from 0 to 5 and then 2 to 4. It's a special case where the boundaries don't depend on the other variable at all. So since all of the 4 boundaries are straight lines, therefore it is a very simple double integral where the integrand is 1 and all boundaries are just numbers. All right, dy dx. When you integrate 1, you get y. So it's y evaluated from 2 to 4 and then dx. Of course, this is just 2, so you get integral from 0 to 5 of 2 dx, which is just 10, because I don't want to write that out, but it's very, very simple, because the antiderivative of 2 is 2x, and then you just plug in 0 and 5 and get 10. Okay, so as I said, this is a very simple example where all the boundaries are straight lines, and then the double integral is just an integral where all 4 boundaries are numbers. Now let's look at another problem. Which is more complicated. Where the upper and lower bounds of not upper and lower, where 2 curves are given and they will intersect at certain points, you have to find the area in between. So find the area between the curves y equals x squared and y equals x cubed. Now, when you're only given two curves, of course, they have to intersect. Otherwise, it won't form an area. So the first thing we do is find intersection. So find intersections. We find the intersection points by formulating the equality x squared equals x cubed. And you get x squared minus x cubed equals 0. Take the common factor x squared, you get x squared times 1 minus x equals 0. So two solutions, x equals 0 or x equals 1. All right, now that we have the intersections, we have to find, determine which curve is larger or higher between the two intersection points, x equals 0 and x equals 1. It can be done multiple ways. You can simply just plug in a number, say 1 over 2, and if you plug in 1 over 2, you get 1 over 2 squared is 1 over 4, while 1 over 1 over 2 cubed is 1 over 8. Since 1 over 4 is larger than 1 over 8, we get x squared is larger than or equal to x cubed when x is between these two intersection points. Or you can just analyze it, since x cubed is x squared multiplied by x and x is smaller than 1, therefore x cubed must be smaller than or equal to x squared. Either way, the purpose of the second step is to determine which curve lies above the other, and if you know that, you can form the double integral. This is step 2. And step 3, form double integral. Right? You need to know which curve is larger between the intersection points, because when you're forming double integrals, you have to use the two curves as boundaries of the integral. And if you don't know which one's larger, you don't know which one is upper bound and which one's the lower bound. So you have to find which curve is larger first. All right, now that we've done that, we form the double integral. Since the curves are functions that depend on x, that means we have to integrate with respect to y first. And as we said, as we found out in step 2, x cubed is smaller, so it's from x cubed to x squared. And then integrand is 1, integrated with respect to y, and then x. The boundaries for the integral with respect to x are just these two intersection points from 0 to 1. If you're wondering about the graph, it looks something like this. X squared and x cubed, like this. Something like that. Of course, it goes on after that, but they intersect here. And this is the area in between. And the lower one is x cubed, the higher one, and the upper one is x squared. All right, let's compute this. The inner integral, of course, just gives us x squared minus x cubed because the integrand is 1. If we integrate this, we get x cubed over 3 minus x to the 4th over 4 evaluated from 0 to 1. Plug in 1, we get 1 over 3 minus 1 over 4. Plug in 0, you get 0. So the answer is 1 over 3 minus 1 over 4, which is 1 over 12. As I mentioned in the beginning, the order of the double integral can actually be changed. From our previous examples, the previous practice problems that we've done, you see that forming the main difficulty in forming the double integral lies in finding the correct boundaries for the integrals, or the correct limits for the integrals. It's not really finding the integrand, because when you're looking for the area, the integrand is always just 1. So the only difficulty is finding the correct boundaries for these integrals. Now, if we look at the previous problem, this one, what we did was, this is not the best graph. Sorry, let me change the graph a little bit. Just because it is a little too steep. Okay, so this little area here. What we did was we consider this x cubed. The higher one, the lower one is x cubed, and the higher one is y equals x squared. What we did was we consider y equals x cubed as the lower bound of this area, and y equals x squared as the upper bound of this area. So we integrate from lower bound to upper bound first, and then we integrate in the horizontal direction, and the left bound is x equals 0, and the right bound is x equals 1. So this is what this double integral represents. We integrate from bottom to top first, and then from left, which is 0, and to the right, which is 1. Now we can also go in the other direction. We can consider, for example, in this case, y equals x squared to be the left bound, right? Because when you look at this interval from 0 to 1, this curve lies to the left of this curve, which is y equals x cubed. Y equals x squared is to the left of y equals x cubed. So who's to say we cannot integrate from left to right first, and then from bottom to top? We can certainly do that. So if we integrate from the left, if we consider y equals x squared to be left bound, and y equals x cubed to be the right bound, then the lower bound would be just y equals 0, and the upper bound will be y equals 1, which is obtained by plugging this 1 into either one of these functions. Okay, so but the only problem is, if we integrate from left to right first, that means we have to integrate with respect to x. That means the boundaries will have to be things that depend on y. They cannot be functions of x. You cannot integrate, say, from x squared to x cubed and then 1 dx. This is incorrect, because what does this integral really mean? The variable is appearing in both the variable to which you're integrating over with, and also it appears in the boundaries, so it doesn't really make sense. So we have to, how do we change this area into an integral with respect to dx first, then dy? And the trick is to find an expression x equals f of y that describes these two curves, which is what changing the order of integration does, which is how we change the order of integration. Let me copy the problem here. Find the area between the curves y equals x squared and y equals x cubed. Okay, first from the previous problem, y equals area is integral from 0 to 1 and then from x cubed to x squared dy dx. Now we're saying we can change the order of integration and integrate horizontally, which is in the x direction first, and then with respect to y. So how do we do that? We notice that the curve y equals x squared is the same as writing x equals square root of y, of course when x is larger than or equal to 0. Because we know we've already computed the points of intersection which have the coordinates 0 and 1. So we are only concerned with the interval between 0 and 1, which means non-negativity for x and gives us the equation x equals square root of y. And y equals x cubed is equivalent to x equals y to the 1 over 3. So now we've rewritten these two curves into well, y equals x cubed is the same as x equals y to the 1 over 3, and y equals x squared is the same as x equals square root of y. So when we want to integrate with respect to x first, our boundaries become from square root of y to y to the 1 over 3. So we have this formulation. Area equals from square root of y to y to the 1 over 3 and dx. Right, so when we are integrating in the x direction first, we look for the left front. We are integrating, that means we're going from left to right because right is the positive direction. When you look at this arrow, it's pointing to the right. The right half of the x-axis is positive. So the right part is the positive part. So we integrate from the left end to the right end. And in this case, the left end is x equals square root of y, and the right end is x equals y to the 1 over 3. Therefore, we have this inner integral. And for the outer integral, we look for the boundaries for the variable y, which is once again from 0 to 1. So this is another expression for the exact same area. If we compute this, it becomes y to the 1 over 3 minus square root of y dy. And y to the 1 over 3, when integrated, gives you y to the 4 over 3, but divided by 4 over 3, so times 3 over 4. And then minus y to the square root of y is y to the 1 over 2, so you get 3 over 2 and then 2 over 3. This whole thing evaluated from 0 to 1. Plug it in, you get 3 over 4 minus 2 over 3. Take the common denominator 12, you get 9 over 12 minus 8 over 12, which is 1 over 12. All right, so this is the same as the answer we obtained in the previous problem. So the moral of the story is we can change the order of integration and get two double integrals which are equivalent, which is this 0 to 1 and x cubed to x squared dy dx equals from 0 to 1 and then square root of y to the 1 over 3 dx dy. Okay, let's do another exercise. Change the order of integration of the integral from 0 to 2 y squared to 4 dx dy. And confirm that the two integrals by two integrals I mean this double integral and the one we will get. The two integrals yield the same value. All right. So going back to our last example, what did we do when we tried to change the order of integration? We first looked at this area and determined the lower bound, upper bound, left bound, right bound, right? So we have to do the same. That means the step one is to graph this area. Okay. Now, let's look at the inner integral. It tells us the lower, since we're integrating with respect to x, it tells us the left bound for this shape is x equals y squared. Now, what does x equals y squared look like? We know y equals x squared is a parabola, so x equals y squared is a parabola facing right. So it's something that looks like this. Okay, so this is the left bound. And the right bound is x equals 4. So something like this, a straight line that intersects with this parabola. Okay, and going to the y direction, not y direction, going to the y variable, the lower bound is 0, and the upper bound is y equals 2. So we have to locate this y equals 2. Now we notice that this intersection is given by x equals y squared and x equals 4. Therefore, 4 equals y squared and y equals plus minus 2. So this one is 4 and plus 2. This one is 4 and minus 2. Right? So the two intersections are given by this. And this coordinate, this point has y coordinate 2. So it lies on the straight line y equals 2. So our upper bound y equals 2 is just a straight line that looks like that. All right, so we have 1, 2, 3, and 4 curves, and the area that's bounded between them is this part. All right, step 2. Now that we have the shape, we can change the order of integration. Change order of integration. All right, the original double integral was dx dy. So we were integrating in the x direction first. X direction means from left to right, and if we want to change the order, we need to end up with dy dx. And if we want to integrate with respect to y first, we need to go from bottom to top. So let's look at what this bottom is. The lower bound obviously is y equals 0. So that's the lower bound. Oh, let me write this. Area equals, the lower bound is y equals 0. Now what is the upper bound? The upper bound is, I should find the upper bound first. The upper bound is x equals y squared. Now the same problem. We need to integrate with respect to y first. So we cannot have y squared in the boundary. Therefore, we need to rewrite this as a function of x. So we have x equals y squared. It is equivalent to y equals square root of x. Of course, when x is larger than or equal to 0. Because we already know what this shape is, so we're not really concerned about the half part, the lower half of the parabola. We only need this part. The upper half is characterized by y equals square root of x. Of course, the lower half is y equals minus square root of x, but as we said, it's not really important here. Okay, so this is the upper bound. And as we said before, the lower bound is y equals 0. So we have the inner integral, which is from 0 to square root of x, and integrated with respect to y. All right, so the outer one is the integral for x. Going in the x direction means from left to right. The left is x equals 0, that we knew. And the right is this straight line, x equals 4, so it's from 0 to 4. All right, let's integrate this. Not integrate this. So this is the complete formulation of the integral in the other order. And step 3, evaluate the two integrals. We need to confirm that these two integrals do give the same value. The original double integral was 0 to 2, and then from y squared to 4 dx and dy. Let's compute this. This is from 0 to 2, 4 minus y squared dy. That's 4y minus y cubed over 3 from 0 to 2. 4 times 2 is 8, and 2 cubed is 8, so 8 minus 8 over 3, which is 16 over 3. All right, the second one, 0 to 4, and then 0 to square root of x, dy dx. This is the integral from 0 to 4, square root of x, dx. Okay, I sometimes have trouble integrating the square roots and stuff. Especially this is probably fine, but when you have a long integrand with square roots involved, it's just hard to get my head around it. But writing square roots as an exponential with the exponent 1 over 2 is really helpful. So it might be beneficial to write this into the integral of x to the 1 over 2 dx. And then the antiderivative is adding 1 to the exponent gives you 3 over 2, and then divided by the new exponent. Divided by 3 over 2 is the same as multiplied by 2 over 3. This thing evaluated from 0 to 4. Okay, plugging 4, you get 2 over 3 times 4 to the 3 over 2. Minus 0, of course. Now, how do you compute 4 to the 3 over 2? You do it one by one. You compute 4 to the 1 over 2 first, and then cube it. All right, because a simple rule is say we have numbers a and b. X to the a times b is x to the a, then this thing to the b. Okay, so we're just using this rule to claim that 4 to the 3 over 2 can be computed by 4 to the 1 over 2 and then to the third. Okay. Now 4 to the 1 over 2 is just square root of 4, which gives us 2. So it's 2 over 3 times 2 cubed, which is 8, so it's 16 over 3. So we've confirmed it. These two double integrals, they do indeed yield the same value, which is expected because they represent the area of the same shape. Okay, so that is all for today. Um, we've completed the basics of double integral. In the next lecture, we will talk a little bit more about. We'll give more applications of the double integral. For example, how to find the volume of a solid, or some other real world examples. All right, so that's it for today. Quiz 2 has already been posted. It's due the end of the day, which is so midnight Monday. And as always, you have 40 minutes to complete and upload.